Hello, friends. Here is a question that trips up a lot of people early on. You need to store a list of values in your program. Do you reach for an array or a linked list? They both hold data, they both let you loop through it, so what is actually different? Here is the mental model to hold on to through this entire video. Imagine you are booking seats at a cinema. An array is like reserving 6 seats all in one row. Every seat is right next to the last. A linked list is like reserving 6 seats scattered across the whole theater, and each person holds a note pointing to where the next one is sitting. Same number of seats, completely different arrangement. That difference in layout is what drives every trade-off we are about to explore. Next up, let's look at exactly how arrays sit in memory. Alright, so let's look at how an array actually lives in memory. When you declare an array, the system carves out one continuous block of memory. Every element sits right next to the previous one, with no gaps between them. That's called contiguous allocation. Now here's why that matters. Each element has an index, starting at 0. Because the elements are evenly spaced, and the block starts at a known address, the computer can calculate exactly where any element sits with a single arithmetic step. It doesn't scan from the beginning, it jumps straight there. That's why reading any element by index takes constant time, or big O of 1, no matter how large the array gets. The size doesn't slow you down at all. Next, we'll see what happens when memory is not contiguous. And that brings us to linked lists. Alright, now let's look at how a linked list actually lives in memory. And this is where things get really different from what we covered on the previous slide. A linked list is made up of nodes. Each node holds 2 things: the actual data value and a pointer, an address pointing to where the next node lives in memory. That pointer is what chains them together. Here's the key shift. Those nodes are not sitting next to each other. They're scattered across memory, wherever space happens to be free. Node 1 sits at address hexadecimal 04, and the very next node is over at hexadecimal 11. The pointer bridges that gap. So instead of one tight block, you've got a chain of individual pieces linked by pointers. No index math, just follow the arrows, one node at a time. Next, let's see how this difference in structure plays out when you insert or delete an element. Alright, let's see where the real difference shows up. Insertion and deletion. Say you have an array holding 10, 20, 30, 40, 50, 60, and you want to insert 99 after index 1. The array has to physically shift every element from index 2 onward 1 position to the right before it can place 99. That is 4 moves here, and in the worst case, it scales with the size of the list. Now do the same thing in a linked list. We covered how each node holds a pointer to the next one. To insert 99 between 20 and 40, you redirect 20's pointer to the new node, then point that new node at 40. 2 pointer updates. Done. No shifting at all. Deletion works the same way. Arrays shift, linked lists just rewire. Next, we'll lay all of this out side by side with the actual time complexities, so the trade-offs become crystal clear. Alright, let's pull everything together into one clear picture. We covered how arrays give you instant random access. That's big O of 1, because each element sits at a predictable memory address. Linked lists have to walk the chain from the head, so access costs big O of n. Now flip it for insertion and deletion. Arrays need to shift elements, which is big O of n. But in a linked list, once you have a reference to the right node, as we saw in the last slide, you just rewire 2 pointers, giving you big O of 1. There is one real cost though. Every linked list node carries an extra pointer alongside its data, so memory usage is higher. Neither structure wins on every front, and that trade-off is exactly what will tell you which one to reach for, coming up next. Alright, so how do you actually decide? Here is the simple rule. If your program reads by index often and the size stays predictable, go with an array. Fast access, tight memory, no overhead. But if you are constantly inserting or removing items, especially near the front, a linked list is the better fit. Those operations are constant time there, versus linear time in an array. The key takeaway from this whole video is that neither structure is universally better. Arrays win on access. Linked lists win on dynamic modification. Know your dominant operation, and you will always pick the right one. That is it for this video, friends. If this helped, give it a like and subscribe to Webronaq for more clear, straightforward explainers. See you in the next one.